Hello everyone, myself Shivam Mishra from MTech second SEM, and I am here to present the topic Cathodoluminescence. Here are the contents of this presentation: introduction, how it works and its importance, how to perform CL imaging, sample preparation and research using CL, and microscopes, CL from SEM, its advantages, applications, detectors, and differences. Now introducing this topic. CL is nothing but the process whereby light is generated if electron beam hits a sample or specimen. Now, also CL is light or electromagnetic radiation which range between the UV and near IR, that is infrared, of the electromagnetic spectrum, and it is generated when the fast electrons beam hits an specimen. Here is the image that is showing that signals emanating from a sample when the electron beam interacts with a bulk sample, and it is the green pear shape, that is this this region corresponds to the generation volume where Cl photons are produced. Now how it works. Here a sample is taken and it is bombarded by fast electrons. The material becomes excited, and as it returns to a ground state, it luminesces in various colors, and these colors reveal various information about the composition of the sample we have taken, and this data can be collected with nanoscale resolution, that is very minute resolution, and can reveal contrast that cannot be observed with any other optical microscopy technique, which makes the CL imaging is a very unique and very useful concept for understanding these type of relations and compositions. Now, why CL is important? Actually, CL emission is used to study the fundamental property of the matter, that is light transport, scattering, band gap defects, resonant phenomena. Here, a CL image of a diamond in SEM, that is scanning electron microscopy, was taken, and it shows that real colors. Here is so beautiful. And now here is the another image, that is CL overlay, and on same image that of an INGAN polycrystal, that is indium gallium nitrogen polycrystal, and the blue and green channels represent real colors, whereas the red channel represents to UV emission. Now CL is also a very uh, CL also prove very good technique in industry, and it also provide very valuable source of information for fundamental research, that is metrology and failure analysis of any industrial goods or product, that is. Now how can we image your CL? First, in a vacuum chamber, a sample of interest is taken, and the electron beam is focused on the sample. Here, the light is generated after the electron beam hits the sample, and it is collected with a collection optic, that is mirror or objective. Now, it can also be captured directly by a CL detector in the chamber. Here is the image of the CL detector that is in the figure, and the light which is captured by detector, it is directed towards the light detection unit. Now, this detector can be used to characterize various aspects of the light signal, that is its intensity, color, and many more, like its composition or various things. Here is a sample preparation used for CL imaging and CL, that is for research purpose. Some criteria for sample, that is sample surface should be flat enough, not rough, and it also have large differences, that is greater than 0.1 millimeter, should be avoided for the sample preparation, and sample also should be conductive enough to prevent charging effects in the same, and if it is not, then coating with the sample with a thin layer carbon or metal works well, that is we have to coat it with a thin layer of carbon or metal to make it conductive enough. Now CL for research, that is CL emission from a rock. Here is the image of a crystal. Now the CL emission from a rock gives insights into the crystal growth, zonation, cementation, replacement, deformation, provenance, trace element, and defect structures. These can be used to fingerprint a rock and reveal interesting spatial textures on a submicron scale, thus making it a very good for research purpose in mineralogy or geology or various other fields. Now CL microscope. Here, a CL microscope combines a regular, that is a light optical microscope being in daily use, with a cathode ray tube. Two types of CL microscope are in use, which is differentiated on the basis of the cathode ray tube being used in the microscope, that is a cold cathode CL and a hot cathode CL. The basic difference between these are the cold cathode CL generate electron beam by a corona discharge tube, whereas in hot cathode CL microscope, the electron beam is generated by an electron gun with tungsten filament. The advantage of the hot cathode CL is that that is the precisely controllable high beam intensity being used in it, which stimulates the emission of light even on the weakly luminescing materials. And in cold cathode CL microscope, it is very simplest and most economical type. It also provides positive ions along with the electrons, which neutralize the surface charge buildup, leading to eliminate the need for conductive coatings to be applied to the specimen. That is, conductive coating is not needed to prevent charging because also provides positive ions along with the electrons, neutralizing the surface charge buildup. Here is the image of the in a hot cathode CL microscope being used, and here is the thin section of quartz from a hydrothermal beam. That is left image here. Left image is of CL and right is of transmitted light. Now here is CL from a SEM, that is scanning electron microscope. Here is the image, and it shows the sketch of a cathodoluminescence system. Here the electron beam. Here the electron beam passes through a small aperture, that is here, and in the parabolic mirror, that is here, and which collects the light and reflects into the spectrometer, that is here, and a charged coupled device, that is CCD or photomultiplier, can be used for parallel or monochromatic detection respectively. Here these both can be used for detection of the light being passed through the spectrometer after passing from the parabolic mirror. Now an EBIC signal system here can be used to may be recorded simultaneously, that is electron beam induced current. Now there are three types of imaging, that is CL imaging can be obtained by scanning the microscope beam in an XY pattern, and an optical activity of the specimen can be obtained, that is the CL imaging. But if we measure the wavelength dependence for a fixed point or a certain area, the spectral characteristics can be recorded, that is just CDL spectroscopy, that is CL spectroscopy, that is cathodoluminescence spectroscopy. And furthermore, if the photomultiplier tube, that is here, is replaced with the CCD camera, an entire spectrum can be measured at each point of a map, that is hyperspectral imaging can be obtained. Here is another sketch, that is sketch of a cathodoluminescence objective inserted into a same column, that is uh, an electron microscope. If used with a cathodoluminescence detector, it provides high magnification. And if an optical cathodoluminescence microscope benefits is that it shows visible color features directly through the eyepiece because the objective is inserted into the same column. So in recently developed systems in these days they tries to combine both optical and electron microscope to take advantage of both these techniques, so that more magnified image can be obtained, because the optical properties of an object is related to the structural properties object with the electron microscope, making it more efficient enough. Now here is the key advantage of CL imaging that make it very different from the others. First, if we are using the electrons as an optical excitation source, it has several advantages like overcoming the diffraction limit, and measurements are performed with an electron microscope environment, which can be used to correlate nanoscale geometrical features with the optical response. That is very minute geometrical features which can be done by the CL. Here is the image. This diagram includes an electron micrograph of a 125 nanometer long gold rod which acts as a nano antenna and is resonant at lambda naught is equal to 750 nanometer. The scale bar is 50 nanometer. The overlaid red circle that is here, it represents an optical diffraction limited spot for lambda naught is equal to 750 nanometer and a numerical aperture is equal to 1. Now the small blue dot that is here, it represents a 5 nanometer electron beam and a magnified image of the area enclosed by the gray dash circle that is here is shown on the right. This image illustrates the limitation of optical microscopy and the importance of electron beam excitation for studying nanomaterials, which shows the advantages of CL imaging. Thus, minute image of the magnified image of the minute area is obtained here, and it shows that CL imaging is different from others and hence more efficient and more uh, valuable for studying and researching more in the more in this type of more in this field and for studying these type of relations. Now its application area can be extended to many fields like in geology. It presents a valuable technique for fundamental sedimentary, metamorphic and igneous rock, that is various rock studies, and also it can be applied studies on pores, precious gems, reservoir rocks and construction materials. Here is the image of an rock. Here is the image of a rock being obtained by using the CL. Now, in nanophotonics, CL imaging is a powerful method for studying optical phenomena at the nanoscale. That is, here is the same image, and at lambda is equal to lambda 600 nanometer, and at lambda at 700 nanometer, various CL image has been obtained, and it is also applicable to metallic as well as dielectric and semiconductor nanostructures. These structures find applications in biosensing, fluorescence enhancement, non-linear optics, low threshold steam generation, LED solar cells, integrated photonics, lasers, and much more, and in various fields. Now, application areas in material science. That is, CL can be used to study ceramics, dielectrics, and semiconductors both in bulk and nanostructure materials, and also it is used to determine their light emitting properties at the nanoscale. It also be useful for many functional materials including scintillators, phosphors, high power electronics, light emitting diodes, diode lasers, and solar cells. Here is the various Mary spectra shows the study of various materials by using the CL, and here is the CL imaging obtained of a ceramic. Here are the detectors. These detectors are being used for the detecting the light coming from the apparatus that being used for the CL imaging. Now here is the detection system that is prepared by Delmic, and here is the compact detection system being used. The advantage of this system is that they are very ideal for the optimal collection and detection of CL emission, enabling fast and sensitive material characterization and the nanoscale. These are designed by Delmic, and they are very good enough for this purpose. Now concluding the CL, that is cathodoluminescence. It is nothing but it is the emission of light in response to electron radiation. It is commonly observed in materials with discrete band gaps in their electron energy distributions, example ceramics, including materials and semiconducting materials. One, it is also the one of the product of the electron beam sample interaction in same and stem, that is scanning electron microscopes and scanning transmission electron microscope. It is also a powerful means of characterizing the microstructures not only of minerals and geological samples but also of modern ceramic materials and also in nanophotonics and material science. Here are the references from which I have taken the content for preparing these slides and preparing this presentation. Now, thank you all for hearing me with patience.